Thank you very much. Thanks a lot for the organizing committee to have me here to report on whatever I have to say. And yes, we talk about evidences for the presence of a supermassive black hole and what makes it really difficult to say whether we have a supermassive black hole or not. So the reason why we are doing this is that we are intimately involved in observations of Sagittarius star, both doing VLBI observations in the radio, interferometry in the infrared with gravity at the VLT, and also we are participating in the EHT observations in the sense that we do parallel observations in the infrared to observe the variability while the radio is going on. In addition, the group is also providing instrumentation to measure supermassive black holes, in particular also Sagittarius star. So we have been building one of the beam combiners for the Large Binocular Telescope in Arizona, and we have been building the two beam combination spectrometers for the gravity experiment on Paranal. And we have also built MIRI James Webb hardware that will fly and will help to do these observations as well. So what we have done and what is the bracket, the braces basically of what I'm going to say is we have thought about whether what good a case is it? What the Milky supermassive black hole, how good a case is it? So we have tried to put that into a framework, and we saw that this is a challenge for both for astrophysics and for the philosophy of science. And that's something that we have written up. So basically, it all starts out with a certain philosophical concept that you have to have in which you can then put your observations and try to do the conclusions. And I've tried to run this down together with you. So basically what people do in these days, philosophers do in these days, if they talk about the validity of a concept, they mostly go through discussions of underdetermination. That means you have to be sure, if you want to say that something is real or not, you have to be sure that your theory is complete. You might be missing something. And you also have to be sure that your data is unique, so that you can distinguish one thing from the other. So this is what is meant if you say underdetermination. And of course, there's also the concept of causation, which we come to make sure that something is really existent. You have to see it in a causal context. An example from history here is, for instance, the acceptance of the existence of molecules and atoms. And that was a very tough thing to do, and basically it means that several ways how to measure Avogadro's constant. And there is a famous saying by Hacking, which was a philosopher of science. He said, if you can spray them, then they're real. Meaning that if you can do experiments with these things, and look at them and change the experimental environment, then you have some evidence for them being real. That brings us also with Hacking to two possible ways of looking at research and proving concepts in science. That is realism and anti-realism. So realism basically is the typical physics experiment. You can walk around your apparatus, you can change the voltages and so on and so forth, so you can actually manipulate the process. Anti-realism, as Hacking said, and he said that astrophysics would belong to that, is you have a pure observational science. So you can only observe things. You cannot fiddle with them. This is, of course, not absolutely true. Astrophysics has some way of doing experiments, and also we have the possibility of doing statistics and getting at the problems in this way. In any case, this is basically part of the scheme as it presents itself to us now. We have astrophysics here. We have the experiment and the theory. They both interact. And we have the concept of underdetermination and realism. And so we can discuss this through these two concepts. But making only statements on underdetermination and realism or anti-realism basically is only saying something about the measuring process, and how you get your information. But this then comes without knowledge of the reality or the nature of the object that is under investigation. So to do this, actually, we have to introduce causality. And there's many ways of doing this, and we went back to the Greeks, of course. And there's the school of Parmenides, the Eleatic principle came up there. This is basically a causal criterion. So they thought about things, whether they are real or not, and they only allowed logical standards of clarity and truth, so that you can actually say something about the causal action you have between the object you're looking at and the observer. So this needs to be, these logical statements need to be made so that there's an acceptance by the researcher's ontology. So this is the Parmenides sense. Of course, it is clear that it's very dangerous to use these scholastic principles and apply them to research here, because you may wind up proving the concept of the existence of something that you're not really interested in that context. That's why the problem here comes about, because the causation is seen as something in real factual time sequence. But you can ask the question, what about numbers? What about mathematical concepts? Are they real as well? Do they exist? Or is only hardware existing and the interaction with it? So in order to get this done, you have to have a softened out Eleatic principle. And that was something that Collivan came up with. And he basically made the point that we cannot only talk about causally active things, but we also have to allow to put in causally relevant things. That would be the reality of mathematical sentences, of physical laws, etc. This, by the way, is very important for the Event Horizon Telescope experiment, because the thing that is between the data and the final image is the von Sitter-Zernike theorem. So that's a theorem on the spatial coherence. And that means that, whether or not you can do imaging depends on that sentence. And so this is, in a sense, real, and it's causally relevant for this whole process. So this does not seem to work the way it should. Interesting. So this is now the complete scheme: experiment theory, the discussion of the observing mechanism, and then the causal concept with the Eleatic principle. So this must now be filled with material from the galactic center to find out whether there's a supermassive black hole or not. And of course, this goes along with necessary and sufficient conditions, so you can formulate this all very nicely. And you have to also combine those necessary conditions then in the end. And you have to do it in a proper way, like this, not in this way, where you maybe do wrong conclusions, or you forget about certain principles or information that has to be linked in. So you have to know very, very exactly what you're doing. You always have to ask, did I do all the conclusions right? And did I consider all the premises? These are some of them that is discussed in the paper. It goes along here seeing light rings, or it goes along seeing the shadow of the supermassive black hole, or finding pulsars close to Sagittarius A star. Do we find them? So all these premises are posed as questions so that you can clearly answer them with yes or no, so that you can set up your network. So these need to be combined to sufficient conditions. So I will present 4 of those, just as an example. They have to do with stars, orbiting plasma blobs, with the shadow of the black hole, and with the possibility of finding pulsars near Sagittarius A star. First example is the stars. So I will argue that right now it is already possible to check out whether the supermassive black hole environment that we have for Sagittarius A star is a real supermassive black hole environment, that is, that there is traces of relativity to be seen there. So as you know, there's a star cluster at the center of the Milky Way, and in the central arcsecond there's about 40 sources that are in orbit, high-velocity sources that are in orbit about Sagittarius A star. So what we, this is not reliable here. So this is 3 sources. This is S2 and 2 neighboring sources. And S2 is the one for which we have a full orbit already, and it goes through periapse about right now, a second time. And the fact is that due to the relativistic character of these sources, they don't go on ellipses. But rather, as you can see here, they go on distorted ellipses. That is, they go on open orbits that are Rosetta-shaped. That means this distortion is characteristic for the relativistic effect. So all one has to do now is figure out how to measure the distortion and parameterize it with some relativity measure. And this is what we did here. We used as a relativity parameter the ratio between the Schwarzschild radius and the periapse distance. And if you do that, and if you use a computer and calculate some artificial stars in the computer, then you can actually measure off the distortions, do the parameterization with the relativistic parameter, and then you can measure, for instance, in the long axis and the eccentricity, the values that you would obtain for the upper half and the lower half of the orbit. And the ratio of those two then is a measure of the distortion. Similarly, you can determine delta omega, that's the periapse advance of these orbits. And now that we have the parameterized fits, and we can now go measure off the data for S2, the star that flies by very closely, and find what the relativity parameter is. And we did that, and we find a number which is very close to the expected value. So the expected value is here, 0006, and we find 0008 to 9. But the question, of course, is how significant is that? And what we did here is from the positional uncertainty, you can basically mock up all possible ways how orbital sections could be arranged with each other if you would be completely dominated by measurement uncertainties. So you can determine these ratios of the long axis, the ellipticity, and the periapse advance, and from there get a good understanding of the uncertainties. And these are all the possibilities for delta omega, for the E ratio, and for the A ratio. And you see a very nice distribution, and this is actually the value that we measured off from S2, which, as you can see, is a 3 to 4 sigma measurement. So at an exactness of 3 to 4 sigma, we can already now say that from the data available that the orbit is rather relativistic than purely Keplerian. So, but the stars bring us not very close, the ones that we know. We can get closer. How can we do this? We can look at blobs that orbit the supermassive black hole, if they exist. And you can look at the light curves of those blobs. Firstly, they are dominated by two effects, by Doppler boosting and by lensing. Doppler boosting sets in rather early along the orbit because you're looking around the corner, basically. And then on the left-hand side of the light curve, there is a shoulder defined by lensing. So a very characteristic modulation. You can see simulated light curves for different inclinations and so on, and you see this lensing shoulder coming up in addition to the boosting peak. So that would be for a blob that stays alive at least for half an orbit, so that you can go through this scenario. We used the four brightest flares at that time, and in addition, I show also here the Ponti flare, which was measured after we published the paper. And you can clearly see that they have on the left-hand side a shoulder which mimics this modulation due to lensing. So the light curves show all the characteristics of a blob orbiting a supermassive black hole very close to the last stable orbit. Now we can use that and actually derive the mass of Sagittarius A star from the light curves measured in the X-ray domain. And this works because the masses relate like the Schwarzschild radii, they relate like the travel times on the orbit, and they relate like the flare times. Yeah. So all you have to do is fit in an unscaled way, in a scaleless way, the flares, scale-free way the flares, and reintroduce the mass by introducing the orbital timescale S. So the ratio between the timescale, the flare timescale in gravitational units to the timescale in seconds, then reintroduces the mass. So you can derive the mass of Sagittarius star. You can do that for each of the individual flares, if one could. This is not very good. You can do this for each of the individual flares, and you do get the right answer, 3 to 4 million solar masses, with a rather small scattering. So and we also applied this to an extragalactic case that works there as well. So basically it means that something in the assumption was correct. So oscillations and or orbiting matter close to the last stable orbit seem to be relevant for the X-ray flares, at least the very bright ones. Example 3, the shadow of the black hole. I'm sure we hear more about this. So on the left-hand side, we see simulations of the shadow of the black hole for a supermassive black hole. And on the right-hand side, we see the same simulations for a boson star. So an alternative scenario, alternative to a supermassive black hole. So this is basically a star that is held up by boson repetitive forces. And you see, it looks very much the same. So that means that by finding a shadow of the supermassive black hole, or by finding a shadow, does not tell you necessarily whether it's a supermassive black hole or not. So you need more information or highly precise observations. Example 3. You can do the same thing probably with gravity. There we will be able to measure the center of motion of a flare, and that will allow us to make statements on the orbital tracks close to the event horizon, close to the last stable orbit as well. And it should also be mentioned that the matter is probably more complicated than that. As we found out in the VLBI experiment that we conducted, where we had 5 consecutive coverages of Sag star at 43 gigahertz, we found an additional component on the left-hand side that occurred after an infrared flare with a time lag of about 2 hours. That would be consistent with a possible component being expelled from the center of Sag star and still during its decaying time being visible here, could be measured. So that would imply that there could also be components that move away from Sag star rather than only orbit. That is also more complicated probably because it turns out that it's very likely that also speckle effects might be important in this wavelength domain where the scattering shield is just getting transparent. So basically it's like the situation 3,000 years ago. This is the allegory of the cave, Plato's cave, and you basically have some light source, be it electromagnetic or be it gravitational waves. You have the supermassive black hole, and you would have to measure what the reaction to that is, and from that deduce what you actually see. Example 4 is the possibility of having a clock orbiting Sag star as a supermassive black hole. That would be wonderful. A clock could be a pulsar. But if you look at the numbers, the density numbers, then you see that if you shrink the volume, the number of millisecond pulsars and normal pulsars goes down dramatically. So it's very unlikely that you find a source that can do that for you. Although it would be ideal because it would allow you to map out the space-time in the vicinity of a supermassive black hole, ideally, so you can determine whether it is such an object or not. So as a synthesis, we now can combine all of these statements to possible sufficient conditions and place them actually in this philosophical concept. So we can fill it up completely, and we have some that work more in the realm of underdetermination. So it's very difficult. It's not precise what you measure, so you can't really distinguish one thing from the other. There's others that work in the realm of underdetermination due to rarity, possibly. So that would mean having a pulsar is a very rare thing, although it would be a very good experiment. And then you can combine those things after discussing the acceptance of underdetermination and realism with the causality principle as we laid it out before. So basically combining the results tells you most likely that it may indeed lead to the support of a confirmation that Sag star at the center of the Milky Way can be identified with a supermassive black hole. But there are challenges involved. There's one challenge for the astrophysics, and that is how clean are the observational cases that may serve as logical entities for the causal criterion test. That's a question that has to be asked. And for the philosophy, there's challenges as well. That is, are all necessary conditions for the proof of existence known and fulfilled? And are there individual conditions that can prove are there individual sufficient conditions that can prove the existence, or are there more than that, and are they risky enough? So all of this has to be looked at with care. And there's a terrible reality, of course, that opens up. That is, the easier, or the better measurable, basically, it's not lots of work that is involved here, that the easier a key observation can be made, the less meaningful and stringent it seems to be. On the opposite is right. The more meaningful and stringent key observations are, the more difficult and rare they are. So finding a pulsar close to a supermassive black hole is nice, but will probably never occur. So the real proof does not seem to be possible. However, the acceptance of the idea can be maximized. So at the end, I would like to show the Melancholia by Albrecht Dürer. So that's an androgyne, angel-like being, looking at a star and having thoughts about something. By now we know what it's thinking about. Namely, it's asking exactly those questions that we posed before. How unique are my measurements? And have I combined them properly to a full statement? So you see, there's more discussions needed and experiments, and also more instruments need to be built and run to fill this diagram up and to come up with forthcoming observations and conclusions. And I would like to use this opportunity to announce a conference that will take place in one of the Emirates in Sharjah in November, and that will have an astrophysics part as well. And some of these questions may be discussed there as well. And in terms of VLBI, that's an interesting place, because if they get an antenna, they would be in between the 2 millimeter VLBI arrays, the Korean, Japanese one, and the Western one that we are talking about. Thank you very much.
Thank you very much for your talk. I was wondering whether you could go back to your definition of realism and anti-realism, because
yes.
Usually in philosophy we consider scientific realism to be the statement that the entities postulated by our best scientific theories are true or approximately true, but the question of whether we can manipulate them or not manipulate them is quite unusual. And in particular, when you say, well, it's real if you can spray it, you would also commit to, for example, Pluto or the sun not being real, because you certainly can't spray them, or you can't manipulate them. So I was wondering whether you could say some more about this.
Yeah, but what is meant with this, basically, as an example, is that you have an experimental setup where you can modify the conditions. So you can control the experiment to a certain extent. And that doesn't seem to be the case in many astrophysical cases, right? You have something, and you have to observe it, and it does something, and you can't manipulate it. And as I said, the only way we have is, we can't look at it from the side and so on. The only way we have is do statistics, look at many of those objects, and derive from them what the actual situation is.
But are you then saying that Pluto is not real, or the sun is not real, because those are exactly the...
No, but they are causally interacting, yeah, and we know that for Pluto very well, because missions have been there, so they are indeed causally interacting, and that's why they are fine in that concept. Okay. So they have made the transition from anti-realism to realism, basically.
If a high school student asks you, what's the strongest reason to believe that we have a black hole in the center of our galaxy, what do you answer?
Well, I would show in some of these cases, right? I cannot give a final proof. As I said, I don't think that one is able to give a final proof, but one can only give very strong arguments, right? And for instance, the fact that the X-ray light curves show exactly the modulation you would expect from matter orbiting supermassive black holes is a very good indicator that a very compact object is there that modifies space-time in exactly that way.
And so the alternative would be a boson star. That's the only
yeah, well, that's
counter-candidate.
I mean, I'm not in boson star camp, yeah, but that is out for a call. They can be very, very compact, and as I've seen, as I've shown, they can produce shadow images very similar to the black hole shadow images that one expects. So it's going to be very hard to prove or disprove what it actually is.
Yeah, thanks, Andreas. This is a great talk. What this made me think is that we can use perhaps the philosophy and the constructs that you made to sharpen how we invest in the astronomical observations. So could we say, for example, that with the decision tree you made, that there are some observations that are more important than others? You know, how would we invest our money going in the next decade
Yeah,
if we wanted to sharpen this case in a dispassionate way?
It is, of course, very clear. The closer you get to the event horizon, or the closer you get to the last stable orbit of whatever, the better it is. So you have to get into this highly relativistic regime with your measurement apparatus. And then you are in the region where you can make a statement, how good it will be. I don't think that, of course, this is some of the things that we have, so we have to do them, that the stars at larger distances, they won't tell you whether it's a supermassive black hole or not. They only tell you it's a heavy mass, very compact. And yes, the mass modifies space-time such that you see relativistic effects, but you could also get the relativistic effects by other compact objects. So to make the decision whether it's a black hole or not, you have to get really very, very close in. So maybe the shadow of the black hole, the shadow of that object, is one way to go. One has to investigate how sensitive how deep these maps have to be to actually see possible differences between a boson star shadow and a supermassive black hole shadow. But that sounds to me like a really tough work to do, but probably not impossible.
There's several more questions, but in the interest of time, I think we have